Hi, everyone. Thank you so much for having me here. I think this is a very inspiring place for the kinds of conversations that we're going to be having. And I guess the formal name of this is a flash talk, so there will be a lot of flashing slides. You can ask questions during the panel. I want to tell you a little bit about what we're doing at QuEra, building neutral atom quantum computers and how we are envisioning the future of data centers for quantum computing. So first of all, we have two very big challenges ahead of us when we talk about quantum data centers. The first one is that we need to get to universal fault-tolerant quantum computation, and this means that our quantum computers need to be big and powerful enough to do things that we cannot do with any other method. So for this, we need to get to logical qubit counts in the thousands with error rates of part in 10 to the 10 or better. And this is for sure going to require very advanced techniques in error correction. The second big challenge that we have is that it needs to be in a data center. And this means that it requires for the system to just work, to be deployable, to not have to have people constantly monitoring it. I mean, you can see here what the monitoring for a power station used to be like. I think that quantum computers will be much more complicated than that, but so they need to be automated. We need to make sure that the systems that we're building are scalable and that they have realistic swap-C requirements. So it's not enough to build a system that needs to take this entire building to do a fraction of solving the problem. We need something that can be deployed at scale. And the last is that we need to integrate this with classical compute infrastructure. Quantum computers will not exist in isolation. We need to learn from the history of how classical computing developed, but we need to also recognize the fact that classical computers are really, really good, and we should combine the powers of quantum and classical. So a kind of abstract picture of our vision for the data center using our computers is the following. Using a single QPU, which is something the size of a dining room table, kind of like the size of a small cluster, we believe that we can get to the type of size for a processor to really be useful as a quantum computer, as a standalone quantum computer. But we need to be able to connect these systems together. And for that, we'll hear much more about the networking side in the next panel, but remote entanglement and the rate of remote entanglement is going to be crucial. In our case, we use neutral atoms. You'll hear more about this in a second, but these are optically active qubits, which means that connecting them through photons, through flying qubits, is very native. And what we need to work on is how do we build these systems so that they can give us hundreds of thousands and millions of qubits and an efficient interface with a networking facility. So in terms of the technology that we use to build our quantum computers, we use neutral atoms. This is a very efficient system in that it doesn't require cryogenic cooling. It uses very well-developed optical manipulation techniques. Some of these results that I'm going to show are from our collaborators at Harvard. Some of the results were already referred to earlier. Neutral atoms have now very high entangling fidelities, which are beyond what is necessary to implement quantum error correction. They are massively scalable in that we can, again, use very highly parallelizable optical control techniques. This picture is an actual single shot that was taken in about 5 milliseconds. Each one of those bright spots is a single atom that is held in vacuum, simply suspended. And we can increase the laser power and increase the number of qubits that we have in our system. We can also move the atoms around, and that enables non-local connectivity, which is going to be very important to implement things in parallel and save on the time resources that we have for running quantum algorithms. In our case, physical scalability also means logical scalability, and this is something that I think is very important to stress, that the ability to build quantum computers is going to come from building efficient logical qubits that have quantum error correction. And for us, being able to create these blocks of logical qubits, move them around, and implement all-to-all connectivity is the thing that enables efficient operation. So this is, of course, an animation of what this would look like with a few logical qubits. But this has not just done as an animation, but also something that has been implemented. And here I want to highlight the pioneering work from the Harvard group that was done in collaboration with us, but really led by Harvard on implementing algorithms with up to 48 logical qubits. These were small quantum error detection codes, so not quantum error correction, but it shows that all of these tools put together really enable something new and really, really powerful that can continue to scale. Now, universal quantum computation requires that we do a universal set of gates. We need to do more than just a NAND, and the kinds of animations and results that you just saw have transversal gates that allow them to do things like entangling gates and single qubit gates. But we know that a big limitation is that we need what are called magic states, that are the thing that actually pushes quantum computing into something that can do very, very complex operations beyond classical. And the initial estimates were that about 94% of the resources in the QPU would have to be devoted to magic state preparation. These numbers have been brought down to about 50%. But importantly, this is something that I don't think we talk enough about. Transversal gates are great, but not everything can be transversal. And magic state distillation, the ability to create these magic states with high fidelity, is the thing that enables the full set of quantum computing building blocks. Now, this is something that we've worked on at QuEra. We want to make sure that we have a fully operating quantum computer that can do everything that we need. And this is an example of how we can prepare suboptimal magic states and combine them through a distillation procedure to improve the quality of the resulting magic state. So this magic state distillation, using, in this case, color codes, looks a little bit like this. Again, this is a video of actual atoms that are being moved to implement first the entangling gates within the logical qubit block to initialize the logical qubit. And this is, again, a logical qubit that is no longer in the 0 or 1 state. It's actually in an arbitrary rotation. And then we can combine these logical qubit blocks, as you see across, to perform the distillation procedure. This leads to a magic state that is better than what was achieved for the injection, and the improvement in the distillation increases with code distance. This is really important. We need to be past threshold to demonstrate that as our quantum computers get bigger, as we start increasing the code distance in our logical qubits, that the performance will improve. And this is what you're seeing right here. So this is the last piece that we needed to demonstrate the full set of operations for a quantum computer. And this shows us that there is now a direct path for fault tolerance in the type of systems that we're building. Importantly, because we can connect qubits in an all-to-all type of connectivity, we are not limited to just the kinds of quantum error correction codes that have been very widely studied, like the surface code. We can now start exploring operation on other types of encodings, like the QLDPC, which should reduce significantly the number of qubits required, physical qubits required to generate high-fidelity logical qubits. This is, giving you a sense of the type of numbers that we would need for a utility scale type of system. With 1,000 logical qubits, could be achieved with about 100,000 physical qubits with the types of fidelities that we know we can get. Now, we are talking about quantum data centers, and I want to show this picture. This is a system that we built in Boston. It was used to actually generate all of the magic state distillation results that you saw. This is our Gemini class system, and it has now been installed in Japan at ICE as part of the ABC IQ project. So this is already an early example of integrating quantum and classical resources, and we're developing that orchestration between a high-performance compute center together with a quantum computer. We have some experience also running systems that are accessible through the cloud in partnership with Amazon Braket, and I think that these are the kinds of activities that we need to start working on very early on to understand what are going to be the challenges that we're not yet thinking about in building large-scale quantum data centers. As I mentioned at the beginning, networking is something that still needs to be demonstrated, and it will be a key component. We have seen this with classical computing, and I would argue that the only reason why we can have the kind of AI developments that we have had in the last few years has been because of the networking that can be achieved in GPUs through particularly the NVLink system. So we need to develop this for quantum computers. This is something that I am really excited to be partnering with multiple people in the, particularly in this room, to solve this challenging question, because this is going to enable moving quantum computing from not just the next stage, but the real large-scale future of distributed computing around the world. That is all I have. Thank you very much.